Welcome to the course on design and analysis of the algorithms. Our today's lecture is going to be an overview of the course, and I want to introduce you to the main problems in the course and also convey a spirit of the course. Let us start with a fundamental question. Given a certain problem, how do you solve it on a computer? For many problems, it is relatively easy to design algorithms that will somehow solve them. However, quite some cleverness is needed in designing algorithms that are also fast. That is, algorithms which give answers very quickly. This will be the major challenge in the course. Our main course goal, as I said, is to design algorithms which are fast. Design of fast algorithms. As you may realize, designing anything, be it computers, be it cars, be it clothes, is an art. Okay? So in some sense, you have to be creative and it cannot be taught, but in some other sense, there are also some very well-defined design techniques which have evolved for this purpose. And the goal of this course is to study these techniques. We will also have lots of exercises in which you can apply these ideas. And our hope is at the end of the course, you will be able to solve algorithm design problems that you may encounter later on in your life. There are some prerequisites for this course, and let me just state them. The prerequisites are that you should be familiar with some programming. You should have done some amount of programming in some common language, say C or Scheme or BASIC. You should also have done a course on data structures, and you should have some discrete mathematics background. As you may see, this is not an elementary course, and this background is going to be necessary for us. Our approach in this course is going to be analytical, okay, in the sense that we'll build a model of a computer, analytical. We'll build a model of a computer, that is mathematical, build a mathematical model. And on this mathematical model, we will be designing algorithms. So we design algorithms and we study their properties. Properties of algorithms on this model. Okay. The whole point is to reason about algorithms. So this is very important. Okay, we want to mathematically prove properties. And we want to prove properties. The emphasis on this course is on the proof. Prove properties about speed, say prove facts about time taken. Okay. All this, so there is going to be a number of things that we have to do. Okay. And of course, there is the whole course for this. Okay. So I want to give an overview of the course. Okay. In the next few lectures, we will develop the basic framework. Okay. What I mean by this is that we'll define the mathematical model. Okay. We'll say what fast means. When I say a fast algorithm, what do I mean? This is what we'll say. Then we will embark on a fairly long stretch which involves techniques for designing fast algorithms. Okay. While doing this, we will also be surveying many problems. So we'll look at problems from optimization, graph theory, some problems from geometry, and also some others. It will turn out that there are some problems which do not really quite respond to our algorithm design techniques. Of course, we'll see many problems for which we can design really good algorithms. Our techniques work beautifully. But there are also some problems for which our techniques do not work so well. And for these problems, a fairly intricate theory has developed over the last several years, 10, 20, 30 years. And this theory is the so-called theory of NP completeness. So we'll be studying this theory as well. Let me now come to the topic for today, the main topic for today. Okay. So today I don't want to be too formal, but I nevertheless want to convey the spirit of the course to you. So here is what we are going to do. We are going to take a fairly simple problem which everybody should have no trouble in understanding, and let me state that problem right away. The problem is, given two numbers, m and n, find their greatest common divisor. So everybody understands this problem? We are going to see two algorithms for this. Okay, one is a very simple algorithm which you probably have learnt in school. It is probably the algorithm that you were taught in 5th standard or 4th standard or something like that, and which probably most of us use to solve this, to find the greatest common divisor whenever we need to, such as when simplifying fractions. Then we'll study another algorithm, and this is one of the earliest algorithms which was ever invented, and this was invented by the mathematician Euclid, whom you might know from plane geometry. Yes, Euclid did invent this algorithm even though there were no computers in his time. So we'll study Euclid's algorithm, and from this we will get a sense of what a fast algorithm is. Okay. You will see that Euclid's algorithm, even though we have not defined what fast is, you will intuitively understand that Euclid's algorithm must be much faster, is certainly much faster than the simple school level algorithm that we are talking about. And Euclid's algorithm is also cleverer, and that makes it more exciting, and that's also again the spirit of this course. So let me begin with the simple school level algorithm for factoring. Okay. So everybody knows this, but let me state it anyway. So basically there are 2 or 3 steps. Okay. Again, let me write down the input is 2 integers, m and n. What we need is the greatest common divisor, which is also the largest integer that divides both. And when I say divides, I mean without leaving a remainder. Okay. So here is what the algorithm will look like. Okay. So step 1, we are going to factorize m. What does it mean? It means finding primes let me call them m1, m2 till mk, such that m is m1 times m2 times all of these. Okay. The next step is to factorize n. Okay. What does that mean? Again, break n into its factors. So, write n as n1 times n2 times till some nj. Okay. Note that the same factor may appear several times, and of course, we will have to write it separately. The next step is to identify common factors. And then multiply and return the result. Okay. We are going to take an example of this and in a minute, and we'll see what exactly these steps do. Let me now state Euclid's algorithm. So I'm going to write this as a procedure. So Euclid is a procedure which will take two arguments, m and n, and I'm going to invent a pseudo language as I go along, and that is again going to be in the spirit of the course. We are not going to be too picky about how we write down algorithms. So long as what I mean is clear to you, perfect, everything is fine. Okay. So you could express your algorithms in the most suitable, nicest syntax, so that it's easy for you to get your meaning across. We'll come to all this in somewhat more detail in the next lecture or so. So what does Euclid do? So the first is a check. So we are going to check whether m divides n. While m does not divide n, we are going to do the following. So first we are going to calculate the remainder. So we are going to calculate r of n mod m. Then we are going to set n equals m, and then we are going to set m to be r. All these steps are going to be done inside the loop. Okay. So that's the end of the loop over here. We will prove soon that eventually this loop will have to terminate. And after it terminates, all that Euclid's algorithm does is to return the value that m has at that point. And that's it. That is all there is to the algorithm. It is not clear when you first look at this algorithm that in fact this algorithm works. It seems to be doing some divisions and taking some remainders, but it is not actually factorizing any of the numbers that you want, whose greatest common divisors you want. So let's now take some examples and see whether or not this algorithm works. So let us first take say a small example where we have m equals say 36, n equals 48. How will we do it using our simple algorithm? Well, we'll factor m. So m is equal to a product of prime factors. So the idea is going to be that we are going to test numbers one after another. So we start with say 2, and yes, 2 is a factor, so we'll write it as 2. So when we divide 36 by 2, we get 18. So in fact, now we have to factorize 18. Well, 2 is again a factor. So then what remains is 9. Now 2 is not a factor, so we go over to the next prime number, which is 3, which is a factor. And then only the factor 3 remains. Okay, so we have factorized m. What about n? Again, we do the same thing. We start with 2. Yes, 2 is a factor. So that leaves us 24. Again 2 is a factor, that leaves us 12. Again 2 is a factor. Okay. So that leaves us 6. Again 2 is a factor, and then that leaves us 3. Okay. So then we want to identify what factors are common. Well, these two 2's are common, okay, and then 1 3 is also common. Okay. So common, the common factors are 2, 2 and 3, and so GCD is equal to 2 into 2 into 3 or 12. Okay, nothing terribly difficult in this. This is all, of course, school level stuff. Okay, so let us contrast this with what Euclid's algorithm does. Okay, so let me bring Euclid's algorithm back. So we are going to start with m equals 36, n equals 48. Okay. So let me write it down as we go along. So does m, we have to check whether m does not divide n. So 36 divides n? No. Okay, so therefore we enter the loop. So now we calculate r equals n mod m. So in other words, r is equal to 48 mod 36, or it is equal to 12. Okay, then we calculate n is equal to m. Let me write down over here that, well, we know that m is equal to 36 and n is equal to 48. So n takes the value that m originally had. Okay, so n is now going to become 36, and m takes the value which r has. So r is going to become 12. So at this point, the iteration has ended. Okay. So at this point, our iteration has ended. Okay. And we are left with m equals 36 and n equals 36 and m equals 12. Okay. But now we have to go and check out the loop again, okay, because, well, that's what the while loop says. So this time n equals 36 and m equals 12, and again we have to check whether m does or does not divide 12. Okay, m or does not divide n. Okay, so does 12 divides 36? This time the answer is yes, and therefore we are going to exit the loop. And in fact, at the end of it, we are going to return the current value of m, which is equal to 12. So we will be returning 12. So let us now compare these two algorithms. So here you can see roughly what the work done by the two algorithms is. The simple algorithm had to do factorizations, then it had to collect common factors, and it had to multiply the factors together and return the answer. Okay. Euclid's algorithm, on the other hand, did one division. So first time it divided 36. It checked if 36 divides 48, which is the value of n that we had. And when it found that the answer was false, the division was not possible, then it took the remainder. Then it simply just exchanged the numbers basically, and then again it did one more division. So I can summarize the work over here by saying that this did roughly 2 divisions. How much work does this do? Well, it calculated these so many factors. So it calculated 4 factors. So it had to at least do 3 divisions to get each factor. Here it calculated 5 factors, so it had to at least do 4 divisions. So it at least did 9 divisions. Probably it did more. Okay, we will see in a quick example immediately where it will have to do many more than these. Okay, so as you can see in this school level very simple factoring algorithm, we use 9 divisions, whereas in this somewhat sophisticated algorithm, we use only 2 divisions. So clearly we have done less work. Okay? And although I have not proved yet that Euclid's algorithm in fact works, you can see that it is returning the correct answer. So, but we'll show later on that in fact Euclid's algorithm does work correctly. So let me take one more example. M equals 434, N equals 966. Okay, so these are somewhat large numbers, and let's see what will happen over here. Okay. So suppose you want to factorize these numbers. First of all, it will take some work, but let us see what the answer is going to be. So M can be written as 2 times 7 times 31. Okay. N can be factorized as 2 times 7 times 139. Okay. What is the answer? Well, the common factors are 2 and 7, and the GCD therefore is 14. Okay. Let us now come back to Euclid's algorithm. So let me write down again. M is equal to 434 and N is equal to 966. Okay. The first step is to compute the remainder of n mod m. Okay. So then R is going to be, according to this step, R is going to be 966 mod 434. Okay. Well, 966 is equal to 2 times 434, which is 868 plus 98, and therefore I can write down R as equal to 98. Okay. After this, we just have to exchange values basically. So now N is going to take the old value of M, so N is going to be 434, and M is going to take the value of R, so which is 98. Okay. So at the end of one iteration of Euclid's algorithm, we have new values of M and N, and these are the new values. So we started off with the values 434 and 966. After one iteration, we have the values 434, 98 and 434 in that order, M and N. So now we just have to repeat the same thing with these new values. So this is the end of the first iteration. Okay. And in the second iteration, we are again going to calculate R equals N mod M. So let us do that. So if we calculate R equals N mod M, we are going to get the new value of R to be equal to 434 mod 98. So we have to do the division over here, and which is, okay, so which is 434 can be written as 98 times 4. So this is 392. So plus we are going to get 42. So R is going to be equal to 42. Okay. Well, of course, when we began this iteration, we had to check whether M does or does not divide N, or whether 98 does or does not divide 434. But clearly it's leaving a remainder, and therefore we will enter this iteration. Okay. After that, we are going to set N equal to M. So the value of M is 98, and M will be equal to R, which is 42. Okay. So at the end of the second iteration, these are the values that we have. Okay. So at the end of second iteration, these are the values that we have. Okay. So N is equal to 98 and M is equal to 42. Okay. So we'll have to go into third iteration. So at the beginning of the third iteration, let me just write down the values. So we have m equals 42, n equals 98. Okay. Again, we are going to check, does m divide n? It does not, and so we will enter the loop. When we enter the loop, we have to find out r equals n mod m. Okay. So that is equal to 98 mod 42. 42 times 2 is 84, so 98 mod 42 is 14. Okay. Then it's just a matter of setting n and m correctly. So n will now equal the old value of m, so this is 42, and m will equal the value of r we just calculated, so it's going to be 14. Okay. So these are the values at the end of the third iteration. So now again we are going to come back and execute this loop, and again we are going to check, does m divide n or not? And this time we will see that 14 in fact does divide 42, and at this point the loop will be exited. And at the end we are going to return the result as m. The value of m right now is 14, and therefore 14 will be returned. So what has happened? We took 3 iterations. So summary of this, all this is, we took 3 iterations. What happened in each iteration? Well, we did 1 division per iteration, and before quitting from the loop, we had to do 1 more iteration, 1 more division, and therefore that took 4 divisions essentially. So Euclid's algorithm for this somewhat complicated problem, m equals 434, n equals 966, where we are asking to find the greatest common divisor of m equals 434 and n equals 966, took 4 divisions. Let us now check what happens with the simple algorithm. So here were the factors that we found. So how many divisions did it take? At first glance you might think that it's only going to take 2 divisions to calculate m and 2 more divisions to calculate n, so which is 4 divisions. But that is not quite correct. To check that there is no factor between 2 and 7, we would require checking for 3, 5 as well. Okay. Now after dividing by 7, we had to check whether 139 is a prime. So that would also involve checking all the numbers until 39. Okay. So that would require substantially many divisions. So here again we require many divisions, many more than Euclid's algorithm. Okay. In fact, you will see that if we take bigger and bigger numbers, factoring them becomes much harder. You will have to do a lot more work. Whereas in Euclid's case, we will just do divisions, and we will in fact show now that as we do the divisions, the numbers will become smaller and smaller, and the algorithm will terminate. So the next topic that we are going to get into is I want to argue that Euclid's algorithm actually works. I'm not going to give a very detailed proof. I just want to indicate the main idea. Okay. The main idea is really a fact about divisibility and remainders and things like that. So let me indicate that. So this idea says that if m divides n, then GCD of m and n must obviously be equal to m, because clearly m will be the largest number which divides both m and n. Okay. If not, then we can write GCD of m and n is the same as GCD of n it is the same as the GCD of n mod m and m. How do you prove this? I will leave it as an exercise. But let me just mention the main idea. The main idea is that suppose G is the GCD, then we can write m as A times G and n as B times G, where A and B are relatively prime. Having written them in this manner, you should be able to just substitute into what we have in the fact, and then you should be able to get that. Actually, the fact itself is very similar to what we had in Euclid's algorithm, okay, the fact that we have written down. Okay. So let me just show you the iteration, the loop part of Euclid's algorithm. So the fact says that if you want to calculate the GCD of m and n, then you might as well calculate the GCD of n mod m and m. What does our loop do? It wants to calculate, we want to calculate the GCD of m and n. It first checks what the remainder is, and then it calculates, the remainder in fact is essentially n mod m, so it is essentially this term over here. And we need, and then it sets m to be equal to r. Okay. Okay. So the first argument is set to r, okay, and the second argument is set to the old value of m. But this is precisely what the fact says. The fact says that if you want to calculate the GCD of m and n, instead calculate the GCD of n mod m and m. So in fact, once we are given this fact, the proof of Euclid's algorithm, the correctness of Euclid's algorithm is at least partially done, because what we have accomplished is that we have shown that as we go through iterations, we will always maintain integers m and n, and whose GCD will be the GCD of the original values of m and n. So this is the invariant that we are going to maintain. So the specific values of m and n might change, but their GCD is never going to change. So let me write this down. So as the loop executes, m and n might change, but their GCD does not. And hence what we have is that we will preserve the GCD, and eventually when we exit the loop, we'll exit with the same GCD. We just established that as the loop executes, m and n might change, but curiously enough, their GCD continues to remain the same. As a result, if we ever get out of the loop, then that will be because m divides n. But notice that even at this point, the GCD will still be the same as the old GCD, the GCD of the old m and n. But if m divides n, then the GCD will simply be n, and that's what we will return. And therefore, in fact, we have established that if the loop in fact terminates, then we will be returning the correct value. Now we want to argue why the loop should terminate, why we need to exit, why we will always exit from the loop. This is actually fairly straightforward. Let us examine Euclid's algorithm again and see what happens in each iteration, so long as the loop is executing. So initially the values of m and n might be taking some values. What are the values of m and n after one iteration? Well, the first step is calculating r, okay? But notice that immediately afterwards we are setting n to have the value m. Okay. So if the original values are m and n, then at the end of one iteration n will have the value m, and what will the value of m be? M will have the value r, so it will be n mod m. So what has happened is that the values m and n have now changed to n mod m and m. Okay. But n mod m, anything mod m, is actually going to be smaller than m itself. So notice that the first argument is always continuously, is going to decrease in every iteration of the loop. The value of m is always going to decrease. How long can it keep on decreasing? Well, it has to remain positive. It cannot even become 0, and it might decrease, it will have to decrease at least by 1 in each iteration. As a result of this, we can conclude that the loop has to exit at some point. And we know that if the loop exits, then the correct value is returned. So that proves that Euclid's algorithm is correct. Our next step is to argue that Euclid's algorithm in fact runs reasonably quick. So the basic idea we want to prove is going to be something like this. Well, before that, we are going to assume, we are going to prove something about calls to Euclid's algorithm. And in doing this, we are going to assume that the first argument that we send to Euclid is always smaller than the second. So this means that we will always call GCD of 36, 48 and not GCD of 48, 36. This is only for the purpose of analysis. Okay? Actually, the algorithm as we wrote will work fine if we make this call as well. If we make this call, you will see that internally we will start with m equals 48, n equals 36, but in one iteration we will be exchanging these values. Okay, the first iteration will only be spent for exchanging these values. So m will become 36 and n will become 48. N will become 48. So then we can as good as assume that in fact we will start off our execution in this manner. So we'll assume in fact that we are not analyzing this, okay, because that only adds one iteration. So our assumption is that we are analyzing calls of this kind where m is less than n. Well, of course, if m is equal to n, then there is no question. So the Euclid will immediately return. Okay. So let me now state the main result that we want to prove. Okay. The main result that we want to prove is something like this. Okay. So if Euclid is called with values m, with values p and q, okay, that is Euclid of PQ is called. Okay, I want to make a distinction between the variables mn and their values. So we'll think of PQ as values and mn will be variables. So we are going to call Euclid with values p and q. Okay, then if p is less than q, then in each iteration the sum of the values of variables m and n will decrease at least by a factor 3/2. So initially, if the sum is 6, then in one iteration the sum must go below 4, become 4 or go below 4. If it is 60, in one iteration it must go below 40 or stay for or become 40. What is the implication of this theorem? This theorem establishes that the sum will drop very, very fast, and in fact the number of iterations, this establishes that the number of iterations is equal to log to the base 3/2 of p plus q. Well, it is less than or equal to. So this theorem will put a good upper bound on the number of iterations that Euclid is going to execute. And therefore, all that we need to do is to prove this theorem, and we have a bound on how many iterations Euclid takes. So our goal now is to estimate what happens to the sum of the values taken by m and n in each iteration. So let's say that we start off the whole process, and at the beginning of the iteration m and n take values p and q. So at the beginning of iteration, m is equal to p and n is equal to q. After the iteration, okay, and I mean just one iteration, let us say m takes the value p prime, n takes the value q prime. So what is our goal? We want to estimate by how much the whole thing drops. So we want to estimate p plus q upon p prime plus q prime. Okay, so if we prove that this ratio is at most 3/2, then we are done. So all that remains now is to express p prime and q prime in terms of p and q. Okay. So for that we'll need our Euclid procedure again. So what does the Euclid procedure do? If it does not terminate, and that is the case that we are looking at currently, then it computes r equals n mod m and then sets n equals m. So in terms of this, the new value of n is the old value of m. So going back to this, the new value of n must be the old value of m. So therefore we get q prime must be equal to p. Okay. The new value of m is the value of r, which is the old value of m mod old value of n mod old value of m. The old value of n is simply q mod m, the old value of m is p, and therefore this whole thing p prime is q mod p. Okay. We need one more fact in addition to all this, okay, which concerns p prime plus q prime. Well, what is p prime plus q prime? P prime is the remainder when q is divided by p, okay, and q prime is p itself. So this is remainder plus divisor and we know that the divisor is strictly less than the dividend. Okay. Divisor in our case is P and the dividend is Q, and we assume that P is in fact less than Q, and therefore we can conclude that this whole thing has to be less than or equal to the dividend. Okay. In other words, this is Q. So here are the three facts that we wanted. P prime plus Q prime is less than Q. Okay. Let me align it. Q prime is equal to P, and P prime is less than Q mod P. Okay. If P prime is less than Q mod P, okay, then I can conclude that P prime has to be less than both, right? In fact, it has to be less than, and it has to be less than P. So now it's just a matter of algebra. We are going to add this and this last inequality, but just to get the terms right, we will multiply this last inequality by 2 times. So if we do that, let me adjust this. Okay. So if we do that addition, we are going to get P prime plus Q prime plus P prime plus Q prime. This comes from over here. The whole thing is less than this P, okay, plus this P plus this Q, but let's take this 2 times. Okay, so therefore we'll get 2Q. Okay. So now it's just a matter of simplifying this. So what is this equal to? This is nothing but 3 times P prime plus Q prime, and we have shown that it is less than 2 times P plus Q. And this is exactly what we wanted. So we have showed that the original value of the sum has reduced by a factor of 2/3. So P prime plus Q prime is less than P plus Q upon 3/2. Okay. That concludes the analysis of the algorithm, and we have been able to show that in fact the algorithm will execute a fairly small number of steps. So let me now conclude this lecture and highlight the main points. Okay. The very first point that I want to make is the difference between the two algorithms. The school level algorithm basically uses the definition. Euclid's algorithm uses some more interesting, deeper properties, deeper mathematical properties of the quantities that we are going to calculate. So we study properties of whatever we are computing, and this helps in designing fast algorithms. Okay. There is also one more point that I want to make, which is that the basic way in which we did this analysis, counting iterations, will be useful in the rest of the course. And the precise details of all of this we will cover in the subsequent lectures. So that marks the end of this lecture.